Hello everyone, and welcome to the Newton's second law pre-lab. In the 3 units we've done thus far this year, we started out by looking at constant velocity motion and how to describe it: position time graphs, velocity time graphs, motion maps, and even a math model. And then in unit 2, we developed the idea of Newton's first law, which helped us explain why things can move at a constant velocity. Namely, that things will continue to move the way they do unless acted upon by a net force. In other words, if things are moving at a constant velocity, then those forces must be balanced. Then we did Unit 3, where we looked at constantly accelerated motion, and we looked again at how to describe that uniformly accelerated motion: position time, velocity time graphs, acceleration time graphs, upgraded motion maps, and a wonderful set of 4 kinematic equations that describe the motion. So now in this unit, Unit 4, we are going to look at why things move with a uniform acceleration. And in fact, we're going to get to the point where we're going to be able to predict what that uniform acceleration will be based on what we're going to call Newton's second law. So, to start out in this lab, we have to brainstorm some variables, some things that affect how much an object accelerates. There's really 2 major things. One would be the net force acting on the object. Remember, Newton's first law says that if there isn't a net force, then there'll be no acceleration. So in this case, if something's going to accelerate, there must be a net force. And then the other thing is mass, how much mass the object has. Now, this is a 3-variable lab, so this is the first time we've done one like that. So this is going to be a little more complex of a situation. We're going to use something called the modified Atwood's machine that we talked about a bit in Unit 2. Named after Robert Atwood, a contemporary of Isaac Newton's. And it's a modified Atwood's machine because one of the objects, a cart, is going to be on a horizontal track. It's tied with a string over a massless, frictionless pulley to some hanging masses here at B. When you let that system go, it accelerates. Now, when we talk about mass, we have to be careful here about what is accelerating. Our mass is a combination of the mass of the cart, which we're calling A, and anything we hang on the string. Both of those things are accelerating, and therefore both of them must be included in our mass, which we're going to call a system mass. Next thing we need to do is to draw a little force diagram of that system. You might remember this from Unit 2. I've taken object B and I've slid it up next to object A. We've basically gotten rid of the effect of the pulley, and we've put the tension in the string inside of the system. And by doing that, it becomes something that we don't have to keep track of. Just like we don't keep track of all of the molecular forces in the cart, we don't have to keep track of the forces between the cart and the hanging mass. And we can do that again because they move together. They're tied together, so they have the same acceleration at all times. So what forces act on this system? Well, the force of gravity, which is a force exerted by the Earth on the masses. The force of gravity on object A acts down. So there's F of GA. Notice the extra little subscript here, which is important because it helps us keep track of what force of gravity we're talking about. The force of gravity on B, now in reality that acts straight down, pulls this mass down. But since we pulled it up next to object A, it's going to act to the right. See if you wrap your brain around that here. So this second force of gravity, because of the way we're writing our system, is going to act to the right. Now object A is being supported by the track, and so there is a normal force acting upward. That normal force has to balance out the force of gravity A, and those forces have to balance because A is not moving up or down. Or more importantly, now that we have the term, we can say that A is not accelerating up or down. It's not even moving. No acceleration, no net force. Forces must be balanced. Now there could be other forces acting on this system. And the big 2 that we could have here is we could have friction. Although we don't have a lot of friction, we've played with these carts before, and you know that they're very low friction, as are the pulleys. But also some of our tables are not exactly horizontal, and so therefore you might get an angle effect in there from part of the force of gravity. So we're going to do something a little fancy here so that we can neglect any frictional or angle of track things that are going on. What we're going to do is you're going to hang a little mass hanger from the end of the string, and you're going to put these little masses on there. You've got a blue box full of masses that go all the way down to 1 gram. So you're going to be able to add masses to the end of the string until when you give it a push, it moves at constant velocity. Why is that important? Because again, if it's moving at constant velocity, it's not accelerating, and if it's not accelerating, all the forces have to cancel out. So basically, by adding the little masses to the end of the string until it moves at constant velocity, we are balancing out any frictional and angle of track effects. leaving us with a system that acts as if it's perfect. And so this is something we're going to do, and this will be in your on your lab sheet as well to remind you how to go about doing that. So this just leaves us then with one force that is unbalanced, and therefore a net force which is equal to the force of gravity acting on object B. If you remember from Unit 2, we know how to calculate the force of gravity acting on some masses. We did it many, many times in that unit. In fact, we did a whole lab on how to figure that out. We know that the force of gravity acting on the masses here on B would be equal to the mass of B times little g. Little g is not gravity. It's, in this case, the gravitational field strength near the surface of the Earth, 9.8 newtons per kilogram. So in other words, we can convert from mass pretty simply to the force of gravity acting on B. And that then is our net force. It's the force that's essentially towing both masses. Whatever this force is making both of these masses accelerate. And we can control how much net force we have just by controlling how much mass we put on the end of the string. We can also control the total mass of the system by how much mass we add in there. So that makes net force and mass both independent variables, and therefore acceleration will be our dependent variable. So that means the purpose of this lab will be to create graphical and mathematical representations of the relationship between the acceleration, the net force, and the mass using a modified Atwood's machine, our first three-variable lab. In other words, we should end up with an equation at the end of this lab that has acceleration, net force, and mass in some combination. That combination will be predicted or developed through the lab. Now, we can measure all of these things. We've already talked about how we can measure the net force simply by converting the hanging mass to a force of gravity. We can measure the total system mass using the electronic balances around the room and the fact that the masses we use have their mass put right on them. The acceleration, we're going to use a data studio file, and this is a lot like the last lab we did with the free fall with the picket fences. We're going to have a velocity versus time graph. If you notice, there's a motion detector on the back end of every one of the tracks in the room. And then, of course, we can find the slope of the velocity time graph, which is the acceleration. So let me open up a sample file here. And this will look like the one you're going to use in the lab, except it doesn't have a start button on because I don't have it plugged in. This is a big graph of velocity versus time. And this is basically what your graph should look like. It should be a fairly smooth looking graph. If you have big jagged points in your graph, it's probably because one of two things. Either something's in the way of the motion detector, like maybe you didn't move your hand out of the way after you released the cart, or the biggest problem is probably the angle of the motion detector. Remember from the labs and activities we've done with the motion detector that if you tilt it slightly back from vertical, you tend to get a smoother graph. So if you can't get it to make a smooth graph, call me over and I can certainly help you. Now let's talk about what's going on with this graph. Here, the velocity is 0. So that is after you've hit the start button, but before you let the cart go. Here, it's accelerating. And if we want to know that acceleration, we have to find the slope. So notice I've turned the linear fit button on already. So if you select those points, we get a slope of 0.363, which means the cart was accelerating at 0.363 meters per second every second. Notice the correlation is a perfect 1. So we have linear data, and you should too. So this is the part of the data we want to select. Right? We want to select all those points. And sometimes, depending on which points we select, we might get slightly different answers, and that's okay. Now this part of the graph is where it's slowing down to 0. So this is where you've caught it. And please catch the cart at the end of the track. Don't let it run into my expensive pulleys and fall onto the floor. What's going on here, though? Notice that at this point in the graph, we have kind of a horizontal line. So that means that the velocity is constant here. Well, how can it be constant if it's accelerating before? Well, if you look at the equipment, what's happened here is, right about here, the masses that are hanging off the side hit the pad on the floor. And once the masses hit the pad, they stop pulling on the string stops pulling on the cart, and it stops accelerating. So this is after the masses hit the floor, but before you catch it and stop it. Right? So those are kind of the three parts of the graph. Before it starts moving, after it's accelerating, or while it's accelerating, and again, you have to select this. then it's kind of moving constantly until you catch it and stop it. And the slope of the graph is the acceleration. Really easy to do multiple trials. Alt minus deletes a trial, and you're set for the next one. And be discriminating with these trials. And if your 3 trials don't match up, do some more until you get a good match. Okay, so one of the things here that we need to talk about is the fact that we have 3 variables in this lab, 2 independent variables. And so that means that we have to do 2 experiments instead of just 1, because anytime you change one variable, you have to keep the other constant. If you change both variables at the same time, you're going to end up not knowing what really affected your dependent variable. So we're going to do 2 labs. Acceleration versus force with constant mass is the first half of the lab, and then acceleration versus mass with constant force. So let me talk you through a few of the things that we're going to do here. First of all, the Data Studio file, as you may expect, is called Newton's second law, and it's a big velocity time graph like I just showed you. Second thing I want you to do is to add all of these masses into the cart. 1 black bar mass, 1 10-gram, 2 20s, 1 50, 3 100s, and 1 200-gram mass. And here they are listed in kilograms. Now, the reason the black bar mass is empty here is because it's supposed to be theoretically 500 grams, 0.500 kilograms, but it probably isn't. So you're going to want to throw it on a balance and make sure you get the right number in here. Right? And then add them all up, and that's the total mass you're putting in the cart. Now, once you have all those masses nicely organized in the cart, you're going to leave them in there. And then you're going to compensate for friction and the angle of the track by doing what we talked about earlier. You're going to add small masses, not from here, but from the mass box onto the string, until when you give it a little push, it moves with constant velocity. In fact, you can even use the motion detector to make sure it's constant velocity. It should be a horizontal line. Once you figure that out to the nearest gram, you're going to leave those masses on the string for the entire lab and don't count them towards anything. Okay? They're not part of this. They're the friction masses. So they're making our system move as if there's no friction and it's perfectly balanced. Now, the hard part of this lab, is to figure out how can we change the force but keep the system mass constant. Well, remember that the force is the force of gravity acting on the hanging masses. So we can change the force by changing how much mass we have on the end of the string. But we have to do that while keeping the system mass constant. So here's why I had you put all those masses in the cart to start with. What you're going to do is you're going to take masses from cart A and move them to cart B. Like 40 grams every time. So you're going to take masses from A and move them to B. By doing that, you haven't changed the system mass. The same amount of mass is in this system. It's just that more of it is now hanging on the end of the string, which means there's more force. So it looks like this on your lab sheet. You're going to move 40 grams or 0.040 kilograms at a time. So you have to be careful here, moving masses from the cart to the end of the string. Also, make sure the string stays parallel as it is here in the picture. So that's the first half of the lab. Second half of the lab, which will probably take you another day to get to, we want constant force, and we're going to change the mass and see what effect it has on the acceleration. Same Data Studio file, same masses into the cart, same process to balance friction again, especially if you're here at a new day. You've got to rebalance friction every day because you never know if the equipment got moved around or changed. Then the way we're going to do this is we're going to keep the force constant by putting 0.1 kilograms, 100 grams, onto the end of the string and leaving it there for the entire part of the lab. So constant force. 0.1 times 9.8, right, is the force. We're going to change the mass by, first of all, taking all the masses out of the cart. We're going to run the first set of 3 trials without any masses. Then we're going to add 200 grams, 0.2 kilogram increments into the cart. You got to be a little careful when using the black bar mass, be precise. Then we're going to keep the string parallel to the track. And we're going to calculate the system mass, which is what you're going to record in your data table and what you're going to graph, acceleration versus mass, by figuring out the mass of your cart, put it on a balance around the edge of the room, add in anything you put in the cart for those trials, and then the 0.1 kilogram hanging mass. So this number is going to change for every set of trials because you're going to keep adding masses in there. Each time you do a page, graph it, call me over to look at your graph and approve everything, and then you can go on to the next page. So this is going to be an exciting lab, I hope, and with a big important result, but you've got to be pretty careful about following all the bullet points. Thank you.